There it is. Okay. ID badges are issued to teachers at a math conference. The identification number is 7 digits. The first 3 digits are single-digit prime numbers. The next 3 digits are single-digit composite numbers. The final digit is a counting number that is a single-digit perfect square. How many ID numbers are possible? It's way too complicated for either of these. Let's do this. Since the first 3 and the next 3 deal with single-digit numbers, let us list all single-digit numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's circle the single-digit prime numbers. Is 0 prime? No. Is 1 prime? No. Is 2 prime? 2 is the first prime number. 2 has 2 factors, 1 in itself. 1 only has 1 factor, 1, just 1. 1 times 1 is 1. 0 has infinite factors because 0 times anything is 0. So the primes are 2, the single digit primes are 2, 3, 5, and 7. Don't pick 9. Sometimes people pick 9, but it is odd and small. But it's got factors other than 1 and 9. It's got a factor of 3. If we box the single digit composite numbers, I will again skip 0 and 1 because by the definition, it's not exactly the opposite of prime. It's numbers with factors other than 1 and themselves. And 1 certainly doesn't have factors other than 1 in itself because 1 is the only factor of 1. 0 doesn't have factors other... Oh, let me not go there. That kind of does fit the definition. 0 is just weird. Look, I'll give you a better explanation for that if you ask me. But at the moment, I can't pull it out of my head why that's not composite. But 0 is neither prime nor composite. 4 is composite. 6 is composite. 8 is composite. And 9 is composite. Okay, I think we're in a good position now to apply the fundamental counting principle. Oh, wait a minute. I might have missed something. The final digit is a counting number that is a single-digit perfect square. All right, so we've still got our single-digit numbers. Now here's where we get into an interesting definition. Counting numbers start with 1, because if you're counting, you start way back when people used to count on their fingers. You would start with 1, 2, 3, 4, 5. So 0 is not a counting number. So when we consider single-digit counting numbers, even though 0 is a perfect square because it's just not a whole number square. It's 0 times 0. 0 squared is 0, of course. But if let me put a diamond around the single-digit counting numbers that are perfect squares. 1 is a perfect square because 1 times 1 is 1. The next perfect square would be 2 times 2, or 2 squared, which is 4. 1 squared, 2 squared, 3 squared is 9, and we're done. Those are the only 3 single-digit counting numbers. Whew, there's a lot going on in this problem. Okay, what's the best color to use here? All right. So we've got 7-digit ID badge. First digit, second digit, third digit, fourth digit, fifth digit, sixth digit, 7th digit. I want to read through it again because I've got a question about whether the digits can be repeated. ID badges are issued to teachers at a math conference. The identification number is 7 digits. The first 3 digits are single-digit prime numbers. The next 3 digits are single-digit composite numbers. The final digit is a counting number that is a single-digit perfect squares. Oh, the very last thing it says is numbers may be repeated. Okay, good. So for single-digit prime numbers, we have circled those in red. So I have 4 choices for the first 3 digits of my ID badge. The next 3 digits are single-digit composite numbers, which we have boxed in purple, and there are also 4. And the last digit of the ID badge will be a single-digit prime, and we have identified 3 of those. So this is 4 times 4 times 4 times 4 times 4 times 4 times 3, which is 4 to the 6th power, which is the same as 2 to the 12th power. So 4,096 tripled is 12,000, and 96 tripled, 100 tripled is 300, but I'm going to subtract 9 from that, so 291. So 4,096 and 291 is 4,381. I don't like my chances of that being correct. I did a lot of quick mental math there. Let's see. I don't see it. I must have messed up something on the mental math. Wait, I want to do this. I was trying to show off, if I'm being completely honest. It failed. That's what I get. 4 to the 6th power times 3 is the same as 2 to the 12th power times 3. See, I know 2 to the 10th is 1,024. So 2 to the 11th is 2,048. And 2 to the 12th is, I just realized what I did wrong, 4,096. So 4,096 times 3, I like to just do it this way. Here's what I'm doing. Here's what I tried to do in my head but failed. 4,100 minus 4 times 3. Because 4,000 times 3 is easy. That's 12,000. 100 times 3 is easy. That's 300. And I just need to compensate by subtracting 12 from all that. So what I really meant to do was 12,300 minus 12, which is 12,288. Correct. 12,288. You're welcome to do that on a calculator, of course, but I like to sprinkle in a little bit of mental math and try to help you build on that foundation a bit from time to time the best I can. All right. 12,288. Oh,